Okay, what is the theme today, first of all? So the theme we are going to learn is we are going to continue learning more maths. And in maths, we are going to specifically talk about factors and primality tests. This is very, very well-known important concepts on which a lot of questions are linked. Okay, finding the factors and checking if a number has certain count of factors or a number is prime and all sorts of things. There are several variations and we will look into those. But we will get started with the simplest one. So what can be the simplest one? So let's say somebody gives you a positive integer n and asks you to simply print all the factors. Print all the factors of a number n. For example, if your number n is, let's say, 20, can you quickly tell me the output? What are the different factors of 20? Factors or divisors, both of them are synonyms. You can use anything, whatever you're interested in. Yeah, that's totally right. So 1, 2, 4, 5, 10, and 20. Did I miss anything? Doesn't look like. Yeah, so these are the factors of 20. So can you write a computer program that takes n as input and prints this as output? How many of you feel confident about being able to write this? So it's super easy, right? Because we know one thing for sure, that factors of a number n, they lie in between 1 to n. The smallest factor is 1 and the largest factor is n. There cannot be any factor which is greater than n. So why not run a for loop from 1 to n and check if there is a number I which divides n. If it divides n, we will print I. As simple as that, right? So this can be the simplest approach in which somebody would say that, hey, let's just write a for loop from 1 to n and just put an if check. If n mod I is 0, so if the remainder is 0, that means I completely divides n. So we will simply print the value I. However, what is the time complexity? As you guys can see, order of n, right? Now there are several ways to optimize it. In fact, uh, so I can see that one of you is saying we can bring it down to n by 2. Of course, we can bring it down to n by 2, and many of you might know why, right? Because see, if you have a number, let's say your number is 450. Okay, so what are the different factors or divisors of 450? So if you go on writing, you'll get 1, you'll get 2, so on and on and on. And at last, somewhere you'll get 450. This is the largest one. Just before 450, what do you have? You have 225. Why? Because 225 multiplied by 2 is 450. Okay, so 225 multiplied by 2 is 450, and 450 multiplied by 1 is 450. So what I can say for sure is that if there is a number n, then in between n by 2 and n, there is vacant space. So in between n by 2 and n, there are no other further factors of the number. And it's common sense, right? For example, let's say you take a small number 20 and you find on number line that what are the factors of 20. You will see 1, you will see 2, you will see 4, you will see 5, you will see 10. And see, if you are taking a look, why this one has come? Because 1 into 20 is 20. Similarly, 2 into 10 is 20. 4 into 5 is 20. 5 into 4 is 20. 10 into 2 is 20. So basically, 10 multiplied by 2 is giving you 20. Now, in between this 10 and 20, you are not going to get anything. So it's better to run a loop only from 1 till n by 2. And then once this loop is over, finally, you can print n also, because n is a factor of itself. So what we are doing basically is we are avoiding the iteration in this part. So if you are avoiding iteration in this part, that means you are avoiding n by 2 amount of iteration. So your complexity kind of comes down from n to n by 2, which is not a major boost in time complexity, but definitely it is better by a factor of 2, right? Can we do something better also? Square root n. Okay. So What is the ideation behind that square root of n? Let us understand that. See, uh, we can say one thing for sure. If there is a number, let's say n equals to 20, the same thing. Now, let's say this is your number line. If 1 is a factor, then 20 divided by 1 will also be another factor. And that is indeed another factor. Like you can see 20 over here. And if let's say 2 is a factor, then 20 divided by 2, which is 10, is another factor. Similarly, if 4 is a factor, then 20 divided by 4, which is 5, is also a factor. And it's common sense, right? Because if there is a number x, which is a factor of n, why it is a factor of n? Because n can be expressed as x multiplied by some constant k, right? So like here, if your n is 20, and if you're saying that 4 is a factor, you're saying that 4 is a factor because 20 can be expressed as 4 multiplied by 5. And the moment you are writing it, it means 4 and 5 both are factors of 20. So if you get 1, along with 1, you can associate 20, which is nothing but n by 1. And if you get 2 along with 2, you can associate n by 2, which is 20 by 2, that is 10. And along with 4, you can associate 5. So it means one thing. What it means that these factors, they are symmetric about something. They are symmetric about square root of the number. And I'll tell you, this is a common sense. This is pretty easy to understand. Let's say you have a number num, okay? And let's say the square root of this number is x. So that means number num can be expressed as x multiplied by x. Now let's say this is your number line. On this number line, somewhere here, you have got x, right? Now it is guaranteed that if this number can be expressed as a into b, and if a is towards the left side, it is guaranteed that b will be towards the right side. It's common sense. Just see, let's say your number is 100. If you can write 100 as 10 into 10, because 10 is a square root of 100. Now let's say this is 10. Now if you pick a number behind 10, any number, let's say 4, then 100 equals to 4 into 25, and this 25 will be found towards the right side of 10. You can also write 100 as 2 into 50. And if 2 is behind 10, then 50 is towards the right side of 10. You can take any other example. Like 100 can also be written as 5 into 20. So if 5 is behind 10, then 20 is towards the right side of 10. So it's like a mirror. You can think of it in this manner, that whatever is the square root of a number, that is just like a mirror. So if there is a factor behind, there is a corresponding factor towards the right side also. So what it actually means is that if there is a number over here, let's say k, which is a factor, then I do not need to look towards this side because I am 100% sure that there will be a corresponding factor num by k. So it means I can just iterate in this segment, which is from 0, which is from 1 till the square root of n. And if I get a factor, the other corresponding factor is simply num divided by k. Is it making sense? How many of you are able to relate to this? So this is one very important idea. And now once you have got this idea, you can very easily implement this. You can simply say that, okay, somebody gives me a number n, asks me to list down all the factors. All that I'll do is I'll say, okay, let me just consider the left half. The left half. So let's say if your number n is 25, you need to only iterate from 1 till 5. That's it. If your number is, let's say, 100, you need to only iterate from 1 till 10. So what you will say is for I equals to 1, I plus plus, and you can put a condition, I multiplied by I smaller than equal to n. So this will ensure, see, this thing can be rewritten in this manner. I smaller than equal to square root of n. So if I'm squaring both the sides, this is what I'm getting. And this is cleaner to write, okay, because I'm not calling sqrt function. So it's the same thing. You want to iterate till square root of n. So this is the way to do that. This is the way to ensure that. Yeah. So you would just say that here, the first thing I'll check is whether this number I is a factor of n or not. Now, if this number I is a factor of n, it is guaranteed that there will be another factor which will be n by I. So at this point of time itself, I will print I and then I will print n by I, both. So this is going to handle printing of all the different factors towards the left side as well as right side. There is just one small catch over here. There's just one small edge case, or maybe you can call it edge case or a catch. What is that? Can somebody tell me? Yeah, sometimes it can happen. In fact, not sometimes, exactly one time it will happen that I and n by I, both of them are same. Yeah. So let's say your number n was 25 and you decided you will iterate from 1 till 5. Now, when the value of I is 5, when the value of I is 5, n by I will also be equal to 5. So that you have to handle. So you can just put a special if check for that. So you would say that, hey, if I and n by I both are same, just print I. Otherwise, print both of them. So this is one simple check that you can put and your job will be done. Not a big thing. So this entire code, what is the time complexity of this? How many iterations will be run? Given that this is the breaking condition, number of iterations will never go beyond square root of n. So this is by far the best approach to list down all the factors. Okay. Now let's move on to one quick question. So let's say you are given an integer n, which is a positive integer, and you have to just tell me if the count of factors of n is even or odd. So you just have to tell me whether the count of factors of n, whether it is even or it is odd. Like, let's take a quick example. Let's say the value of n is 6. Can you tell me what should be your response? Should it be even or odd? Yeah. So if you list down the factors of 6, they are 1, 2, 3, and 6. So how many of them are there? 4 of them are there. And 4 is an even number, right? You can take another example. Let's say you take n equals to 9. What will be the output? So what all are the different factors of 9? 1, 3, and 9. There are 3 of those, and 3 is an odd number. So the response is odd. So does everyone understand the question? How many of you perfectly understand the question? So many of you are saying that it will be odd for those values of n which are perfect square. Like n is a perfect square. Here 9, this number 9 is a perfect square, right? 9 can be written as 3 square. And hence you are saying it is odd. But 6 is not a perfect square. So your approach is basically saying that if the number is a perfect square, response should be odd. If number is not a perfect square, response should be even. How many of you agree to this approach? But most importantly, what is the logic behind it? So if you dive deep into it, you don't have to dive a lot deep because I just explained it here. I explained it saying that the factors are symmetric about square root of n. They are all symmetric about square root of n. So that point highlights this fact that if there is a number, let's say 16, which is a perfect square, because it is a perfect square, what is the square root of it? 4. So 4 will exist somewhere here. Now, if there are k factors behind, there will be k factors here. So total number of factors will be k plus k, which is 2k, plus 1, which is this. And 2k plus 1 is always an odd number, right? Like you can see, behind you have got 1, 2, right? And what are the things that you have got over here? You have got 8 and 16, right? And now I mean, as opposed to it, if there is a number which is not a perfect square, like let's say if the value of n is 15, the square root of 15 is how much? It is smaller than 4, right? So it is 3 point something. 3 point something is not an integer. So it will not lie on integer number line. It will not lie on integer number line. I mean, I can just draw a line for it like that. So as many factors you have behind it, those many you will have ahead of it. So if this is k, this is also k. So the quantity will be 2 into k. So super simple approach for solving this question is you just have to check whether the number given is perfect square or not. If it is perfect square, then the response will be odd. Otherwise, the response will be even. It's quite helpful to solve some really tricky question. It looks very easy, but trust me, I'll show you some questions which might be of very tricky nature. And this simple idea will be able to solve those. Okay. Um, so now that we have learned this thing, let's move on and let's take a question. It's more like a puzzle. Okay. So listen to the puzzle very carefully. So there are n doors. Okay. And all the doors are initially closed. This is very important. Initially, all the doors are closed. All right. And these doors are numbered. So let's say the value of n, if the value of n is, let's say, 8, then this is your first door, this is your second door, this is your third door, this is your fourth door, this is your fifth, sixth, seventh, eighth. These are the doors, and because they are initially all closed, so I'll say they are all closed. Okay. And now we are playing a game. Okay. So in this game, there are n rounds. Okay. There are n rounds. What do we do is that in the ith round, we toggle the state of all those doors that are multiple of I. So in the ith round, we toggle the state of all those doors. What is the meaning of toggle? It simply means that if the door is closed, open it. And if it is open, then close it. That is what we mean by toggle. So when we are playing ith round, we are toggling the state of all the doors that are multiple of I. Okay. So let me just, there are n rounds, right? So let me get started with the first round. So let's say I'm doing the first round. So initially all the doors are closed, right? So you have closed 1, closed 2, closed 3, closed 4, 5, 6, 7, 8. In the first round, we are going to toggle the state of all the doors, which are multiples of 1. So can you tell me how many doors are multiples of 1? When I say multiple of 1, their ID should be multiple of 1. So initially all of them, yeah, all of them are multiple of 1 because 1 is a multiple of 1, 2 is a multiple of 1, 3 is a multiple of 1, 4, 5, 6, 7, 8. All of them are multiples of 1. So all of them will have their states toggled. So once their states are toggled after the first round, how will things look like? Open 1, open 2, open 3, open 4, 5, 6, 7, 8. Then we will move on to the second round. In second round, what we will do is we will toggle the state of all the doors that are multiples of 2. Which doors are multiple of 2? Can you quickly highlight those? 2 and 4, 2 and 4 and 6 and 8, right? So we will be toggling their states. So from open, these doors will become closed. So it will become like close 2, close 4, close 6, close 8, and everything else will stay open. When we will play our third round, we will toggle the state of all the doors which are multiples of 3. So which doors are multiples of 3? You have got 3, you have got 6. So their states will be toggled. So when I say their states will be toggled, O3 will become C3 and C6 will become O6. We are toggling, right? Everything else stays exactly the same. And then we will play the fourth round, right? And in the fourth round, we will toggle the state of all the doors, which are multiples of 4. So we will toggle this and that. So C4 will become O4, C4 will become O4, and C8 will become O8. Everything else stays exactly intact. Fifth round, we will toggle states of the doors, which are multiples of 5. So which doors are multiples of 5? Only this one, 5, right? So from O5, it will become C5. Everything else will be exactly alike. Sixth round, we will toggle states of the doors, which are multiples of 6. How many multiples of 6 do you see? Only one, which is O6. So O6 will become C6. Everything else stays the same. Okay, we are just about to end. Seventh round, we will toggle this. O7 will become C7. Everything else is quite intact. And then eighth round. In the eighth round, what will toggle? O8 will become C8. Everything else stays intact. Okay, all right. Game up. After the game is up, how many doors are open? How many doors are open after the game is up? You can see 1 is open, 4 is open, everything else is closed. Okay, so that is what the question is. The question is, if you are playing this game with n doors, then once the game is up, how many doors will be open? That's what you have to say. So what can be the way to solve this question? Some of you have already listed down the solutions. What would others like to say? One way is to play this game. So one way is to just play this game in which, in every iteration, in ith iteration, you will run a loop which will toggle the state of ith door, 2 into ith door, 3 into ith door, so on and on and on. But the time complexity of this will be very high if n is very large, right? So imagine if n is around 10 power 18. So you won't be able to solve it like that. So is there a pattern that you can see? Yeah, so one of you is mentioning it and mentioning it quite rightly that, hey, the doors that have remained open, they are perfect square. Like this 1 is a perfect square. 4 is a perfect square. Is there any other perfect square? From 1 to 8, apart from 1 and 4, is there any other perfect square? No, not at all. Right? So see, your solution should not be based on observation, it should be based on logic. But if you're observing, then that's great. That's very great, but let's put the layer of logic on top of it. So what is the logic here? Tell me one thing. How many times a door, how many times a door is toggled? A door is toggled as many times as is the count of its factors. It's common sense, isn't it? Just imagine. In the ith round, you are toggling the multiples of I, right? Whatever are the multiples of I. So if you talk about something like 6, if you talk about something like 6, it would get toggled in the first round because 1 divides 6. It would get toggled in the second round because 2 divides 6. It would get toggled in the third round because 3 divides 6. Would it get toggled in the fourth round? Would it get toggled in the fifth round? Would it get toggled in the sixth round? Yes. In seventh round? No. In eighth round? No. So how many times it will get toggled? Tell me. It will get toggled 4 times, right? And what is 4? 4 is the count of its factors. Now tell me one thing. If count of factors of something is even, If count of factors of something is even, that means the door would get toggled even number of times. So if you toggle something even number of times, it will remain closed. Imagine if a door is closed and if you toggle it 2 times, you are making it closed to open and then open to closed. If you're toggling it 4 times, then again open, again closed. But if you're toggling it odd number of times, then finally it will be open. So imagine a door was closed and you toggled it only once, so it is open. And if you toggled it thrice, it is open. If you toggled it 5 times, it will still be open. So all that I can relate is if count of factors is odd, then that door would be open. Otherwise, it will be closed. What we just learned before it was that count of factors is odd only for perfect squares. So I can say as many perfect squares are there from 1 to n, those many doors would be open. Everything else would be closed. How many of you now completely understand this logic? So now there is nothing special that you need to do to solve this question, because all that I would say is no matter what is the value of n which is given to you, yeah, the problem completely reduces to counting how many perfect squares are there in between 1 to n. So if your value of n is, let's say, 90, can you quickly tell me how many perfect squares are there in between 1 to 90 without checking everything? So what is the square root of 90? Approximately how much is this? Tell me. Perfect. I mean the squares, the square root of 90. If you compute the square root of 90, it will be equal to 9 point something, right? So what I can say for sure is that the numbers like 1 square, 2 square, 3 square, so on till 9 square will definitely lie in this range. Yes or no? You can see that quite clearly. 1 square is 1, 2 square is 4, 3 square is 9, 9 square is 81, 10 square will not be there. So what it means? It means whatever is the square root, I mean the floor, whatever is the floor of the square root, that would denote that how many perfect squares are there. So just compute the value of SQRT of n and that will be your answer. That's it. Nothing else needs to be done. Okay. So now the second part which we will touch, and both these things are going to be very much related. Okay. So the first part I have just given a logical finishing touch to it, but it will come back. Okay. It will come back. But before coming back, I need to touch upon primality tests. What is the definition of a prime number? What is a prime number? Yeah. Something that has how many factors? Exactly 2 factors. This exactly word is important. Exactly 2 factors. Is 1 a prime number? Can I call 1 a prime number? No, because how many factors are there of 1? Only 1. So 1 is not a prime number. Okay. But is 2 a prime number? Yes, definitely. Is 3 a prime number? Yes, definitely. Is 4 a prime number? Not at all. 4 is not a prime number, right? So I believe all of you understand the meaning of prime number. All of you would already know about it. Okay, come to the main point. The important thing is somebody gives you a number n and asks you to check if it is prime. How would you do that? Sieve of Eratosthenes. Okay, sometimes it can be overkill. In questions like these, sieve of Eratosthenes would perform worse. Okay, so in questions like these, we can use the simplest approach and that performs the best, which is to just count how many factors are there. Yeah, exactly. Just count how many factors are there. And can you do that? Have you just learned how to do that? You can just iterate for this number. I mean, and in what range you will iterate? Tell me. You will just want to iterate from 1 till SQRT of n. So just iterate from 1 till SQRT of n and then check in this range how many numbers you have got which are divisor of n. And if, I mean, like, let's say I mean, of course, when you are checking if I is a divisor, then there would be another divisor, which is n by I. So you can basically count, right? You can count. If the count that you have gotten is exactly equal to 2, in that case, you would say that, hey, this number, it has only two divisors and hence it is prime. Otherwise, you would not call it a prime number. Like for example, I mean, anything that is given to you, let's say you have been given 17. So in case of 17, you would say, hey, let me only iterate from 1 all the way till how much? Square root of 17 would be 4 point something, right? So 1 till 4. So if you iterate from 1, 2, 3, and 4, 2, 3, and 4 are not dividing this. 1 is dividing this. So you would say 1 and 17 by 1, which is 17. These are the two factors. So you would do count plus equals to 2. So finally, you would see that your count is only equal to 2. And that way you would say that this is a prime number. But if let's say instead of 17, it was 18. In that case, at 1, you would have got 1 and 18. And at 2, you would have got 2 and 9. And at 3, you would have got 3 and 6. In fact, many, right? So in that case, the count would not have remained 2. It would have remained something greater than 2. So what will be the time complexity of this approach? Because you are just iterating in this range, which is from 1 till square root of n. The time complexity of this approach will be order of square root of n. Now, let me make it very clear. Those of you who were talking about sieve of Eratosthenes, sieve of Eratosthenes, the pre-computation step of that itself costs n multiplied by log of n. It costs this much. Now tell me which is better. Is this thing smaller or is this thing smaller? This thing is smaller because this is n multiplied by something. Square root of n is smaller than n. So this thing is smaller. So if you just have to check if a particular number is prime, I reiterated. If you just have to check if a particular number, one number, just a single number is prime or not, go with this approach, which is brute force. But if you have to check for a range, that how many primes are there in a given range, their sieve of Eratosthenes will be much more helpful. So we will come to this. By the way, before that, can you tell me how many of you are new to sieve of Eratosthenes, or you have studied but you don't remember or something like that? How many of you need a good introduction to this? You can just write yes. Okay. This is a beautiful algorithm, and there are so many problems that are kind of solvable using it. Okay, so let's understand like what the idea is. So idea comes from this. If somebody tells you that, hey, you print all the primes in the range, I told you range, right? Print all the primes in the range 1 to n. Can you somehow do it? Whether you know sieve of Eratosthenes or not, can you somehow do it? You can, right? Because you just learned a logic to check whether a particular number is prime or not. So what you can do is you can iterate on this range. So you can say, let me iterate on this range, x equals to 1 to n. And for every number x, I will call a function check prime. And we have just learned check prime, how check prime works. So check prime would iterate from 1 till square root of x, find the count on, and based on that, it would give us the result. What will be the worst case time complexity of this? I mean, just an upper bound. If you have to think of an upper bound to the time complexity of this, how much would it be? So this loop is running for n times. And this thing in the worst case would take square root of n time. So I can say the upper bound is n into root of n, which is n raised to the power 3 by 2. And it would give you TLE. If the value of n is very high, it would definitely give you a TLE. So here what a lot of people do is they go ahead with the idea of building sieve. What is the literal meaning of sieve? Have you ever found it in dictionary? So sieve is just like a filter kind of thing, something, something like a filter, where you probably pour, let's say you're pouring a lot of numbers, you're throwing a lot of numbers from 1 till 10 power 5, and what comes out are just prime numbers. Okay, so just how you make tea, right? You pour entire tea and residue is stored here, only the liquid comes out. So, okay, so how does the sieve behave basically? Let's talk about it. So the idea is, let's say you have been given some number, n is equals to maybe 20. So we say that let me list down all the numbers from 1 to 20 somewhere. So I list down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, before we run some simulations on top of this, answer me one very simple thing. It's a simple question. Okay, let's say there is a number. That number is k. Okay, that number is k. Of course, it is some positive number. Okay, now from 1 till k minus 1, from 1 till k minus 1, there was no factor of k. I mean, nothing from 1 till k minus 1 was a factor of k. Okay, I mean, I can say one thing for sure that of course this one is a factor, but it is an exception. It's a global. So let me just remove it for simplicity's sake. Better to say from 2. 1 is a global factor, right? So let's consider from 2. Let's say from 2 till k minus 1, there are no factors of k. Does it mean k will definitely be prime? Of course, right? Because what is the you know identity of prime number? The identity of prime number is that the only factors are 1 and this. So if from 2 till k minus 1 you could not find any match, you could not find any factor, for sure it is prime. This is the idea behind sieve of Eratosthenes. Okay, so what sieve of Eratosthenes does is, now you will understand a lot. If you have got this idea, you will understand a lot. Otherwise, it feels mechanical to a lot of people. So in sieve of Eratosthenes, we list down all the numbers from 1 till 20, and then we first cut 1. Why we cut 1? Because I told you 1 is a global factor and it is not a prime. So we cut 1. So basically when we are cutting something, it basically means that is not prime. Now, whatever remains, in that, the first number which is not cut yet, will definitely be a prime. Why? Going by the same logic. Because if I just re-simulate this logic and tell in this manner, that let's say the value of k is 2 and this is 1. Now, in between, if there is no factor of 2, no divisor of 2, it is guaranteed that 2 is a prime. So with the same logic, I can say that, hey, this 2 for sure is a prime. Now, a number which is prime, all the multiples of it will be non-prime, will be composite, right? Because 2 into 2 will be a composite number, 2 into 3 will be a composite number, 2 into 4 will be a composite number. So what I'll do is, I'll cut all the multiples of 2. So what are the multiples of 2? 2 into 2, 2 into 3, 2 into 4, 2 into 5, 2 into 6, 2 into 7, 2 into 8, 2 into 9, 2 into 10. Right? Okay. Now, again have a look. The part which is remaining, in that part, the first number which is not cut yet, will definitely be prime. Because see, what really happened? If it has not been cut, why it has not been cut? Because it did not have any factor in between 1 till here. 2 was not a factor of it, because had it been a factor, it would have cut it. So whatever remains, in that, the first number which is not cut, if it is not cut, it clearly signifies that it's simply not cut because of the fact that there was no factor of it. Because if there was a factor, it must have been cut. Right? That's the simple idea. So I would say that, hey, this 3 thing is also a prime. So I'll mark it as a prime, and then I will cut all the different multiples of it. So what are the multiples of 3? 3 into 2, which is already cut. 3 into 3, 3 into 4, 3 into 5, 3 into 6. Done. Now again, as I told you, whatever is left, in that, the first non-cut number, what is the first non-cut number? What is the first non-cut number in this part? It is not 4, it is 5. It is 5, right? So I can say that 5 is definitely a prime. See, if you meet a number which is cut, which is marked as a composite, you don't need to do anything. You can simply skip it. You don't even need to cut the multiples of it. Why? Because the multiples of 4 would definitely have been the multiples of 2. They would already have got cut by 2. So you don't have to worry. So skip all the cuts. So now when you land at 5, you say that, hey, 5 is not cut. So definitely this 5 is a prime number. And now I'll cut all the multiples of 5. So what are the multiples of 5? 5 into 2, which is cut. 5 into 3, which is cut. 5 into 4, which is cut. And then 6 is cut, it is composite. 7 is not cut. So it is guaranteed that 7 is a prime, and I'll cut all the multiples of 7. So what are the multiples of 7? 7 into 2, which is 14, it's already cut. And then the next one which you will get is 11. 11 is prime. You will cut all the multiples of 11. There are no multiples of 11. And then 13, 17, 19. So what will happen is that you will be able to capture all the primes. You'll be able to capture all the primes. Whenever you find a number which is prime, you immediately discard all the composites, which are all the multiples of that. That's the basic idea over here. So whatever number space remains in that, the first number which has not been cut yet, it is guaranteed to be prime. And that's how you kind of keep moving. Did you get an idea? Did you get some high level idea around how sieve works? So when you have to implement it, even the idea of implementation would be very, very simple. I'll show you, and let me give you some ideas around it first. So what people usually do is they create a vector is prime of size n by 1, and they mark everything as prime. Initially, they mark everything as prime. And then they say that 0 is not a prime, so mark it false. 1 is not a prime, so mark it false. So 0 and 1 have been cut. And now they iterate from 2. They iterate from 2 onwards. And then the logic is to check if I is prime. If they see that this number I is prime, then what they do is they simply cut all the multiples of I. That is how they move on. Okay. Okay. Talking about it, there is one small optimization that we can do over here. But before that, can somebody talk about the complexity of this approach? I mean, if you just refer to this simulation where so let's say we were at 2, we were cutting all the multiples of 2. We were at 3, we were cutting all the multiples of 3. 4 was being discarded, 6 was being discarded. So if you try to list down the number of iterations, you would say that when you are at 2, how many iterations you will do? You will touch 2, you will touch 4, you will touch 6, you will touch 8, so on till 20. So you are touching numbers in steps of plus 2, plus 2, plus 2, plus 2. So can I say number of iterations will be n by 2, right? When you are at 2, you want to touch all the multiples of 2. So the number of iterations will be n by 2. When you are at 3, how many iterations will be there? So if you are at 3, you will be touching 3. So you will be touching 6, 9, 12, which are the multiples of 3, right? So how many multiples of 3 will be there? The multiples of 3 will be n by 3, right? When you are at 5, you will discard 4. No iteration at 4. At 5, n by 5. At 7, n by 7. So this is the sum that you are going to get. It is equal to n by 2 plus n by 3 plus n by 5 plus n by 7. If you take n common, then inside you will get the sum of reciprocal of prime numbers. Did you hear what I said? Sum of reciprocal of prime numbers. And this thing, mathematically, this series converges to log of log n. You can remember this one now, log of log n. And because of that, the complexity is n multiplied by log of log n. This is one important series to remember. The sum of reciprocal of prime numbers, it converges to log of log n. There is one more important series. So if you have been given something like 1 by 1 plus 1 by 2 plus 1 by 3, which is sum of reciprocal of natural numbers. Sum of reciprocal of n natural number. How much does this converge to? Anyone who would like to talk about it? This converges to log of n. Yeah, that's right. And you will see this. This will also be instrumental at some point of time. Okay, let me show you the code for sieve. See, in this question, what we had to do was, if you read this question, it says, given an integer n, return the number of prime numbers that are strictly less than n. So how many prime numbers are there in between 1 to n minus 1? Because they are saying strictly less. So see what I did. As I said, I created a vector of Boolean is prime. Now is prime of I denotes whether I is prime or not. Okay, so I created this of size n plus 1 because I want to record for all the numbers from 1 to n. So I created it of size n plus 1, the last for the last index to be n. And I marked everything true. 0 false because 0 is not prime. 1 is also not prime. And then I started iterating from 2. And let's look at this logic first. Line number 8. I'll touch upon the other parts, but let's look at this. If is prime of I, so if I is a prime number, then what we are doing is we are cutting all the multiples of I. All the multiples of I. Now here you can see, so it might come to your mind that, hey, the first multiple should be I into 2, and then I into 3, and then I into 4. But here I'm starting J from I. So I'm starting from the ith multiple of I instead of starting from second multiple of I. And why I'm doing that is because, do you understand why I'm doing that? Because think of it in this manner. Let's say when the value of I was 2, you must have discarded 2 into 2. You must have discarded 2 into 3. You must have discarded a lot of things like 2 into 7, 2 into 8, and so on and on, right? Now, the moment the value of I becomes, let's say 7, when the value of I becomes 7, would you be interested in discarding 7 into 2? No, because 7 into 2 is already discarded by 2 into 7. Similarly, would you be interested in discarding 7 into 3? No, because that would already be discarded by 3 into 7. When the value of I would have been 3, it would have discarded 3 into 7. So it's better to always start from the ith multiple of I. So if the value of I is, let's say 7, I'll start from 7 into 7. Because 7 into 6 would be done by 6 into 7. And 7 into 5 would be done by 5 into 7. When the outer loop would be 5, it would be cut as 5 into 7, right? So this logic is written. So we are starting from the ith multiple. And so j is initially equal to I, j plus plus, and we are going as long as I into j, which is my number, is smaller than equal to n, because I just need to find the primes in the range from 1 to n, right? And even this thing has been run only till square root of n. Now why? I mean, it's a common sense. It's a common sense because let's say you are interested in finding the primes from 1 till 100. So if you are interested in finding the primes from 1 till 100, the moment value of I becomes 10, you would have considered 10 into 10, which is 100. Now, if the value of I becomes 11, you don't want to consider 11 into 11 because that is greater, right? For each number, we start from num into num, and then we go to num into num plus 1 and so on and on. So we have done this because it helps us to save so many iterations. It helps us to save so many iterations and gets our job done pretty easily. And this is nothing but a pre-computation, right? Because you have pre-computed for each number whether it is prime or not, right? See, second loop, the idea is Let's say the value of I becomes 5. Then when I showed you the simulation on my notepad, I said let's start from 5 into 2 and then 5 into 3 and then 5 into 4. But it doesn't make sense to start from 5 into 2 because 5 into 2, which is 10, was already discarded by 2 into 5 when the value of I was 2. Similarly, 5 into 3, which is 15, was already discarded by 3 into 5 when this thing was 3 and 3 was prime and this loop was running. So the first number which you should start with should be 5 into 5, right? So this inner loop is starting from the ith multiple of I instead of starting from the second multiple of I. And then this condition you understand, right? Because we don't want to hit a number, we don't want to check the primality of a number which is greater than n, right? We just declared this to accommodate numbers from 1 to n. So this is the termination condition. So once this loop is run, we know for each number I whether it is prime or not, right? And now in this question, I had to count how many primes are there in between 1 to n minus 1. So we know that 1 is not a prime number. So we ran our loop from 0 to n minus 1. And if ith number is prime, we do answer plus plus and finally we return the answer. The total time complexity of this approach is n log of n. So this is the implementation of sieve of Eratosthenes. Does it make sense? How many of you understand? Let's jump on to another question. There is a special category of numbers which is called as T prime. Listen to the question and then we will talk about it. T prime is that number which has exactly three factors. Exactly three factors. Can you give me some example of T primes? 4. Okay. Okay. All right. Very good. So now the question is that you have an array. Let's say your array contains 10, 1, 3, 16, 20, 25, so on and on. And 36. There are many numbers. All right. So you have to tell me which numbers are T prime. Okay. Which numbers are T prime. So can you tell me which of these numbers are T prime? 25. The factors of 25 are 1, 5, and 25. Factors of 16 are 1, 4, and 16. So those of you pointed out to 16, you missed out on things like 2 and 8. So this is not T prime. Yeah, this is not T prime. So 25 is a T prime. Apart from 25, is there any other number which is a T prime? So what is the attribute of a T prime number? How do you recognize whether a number is a T prime or not? And what is the logic behind it? Let's first talk about the logic, not the solution. Can I say that for any number, listen very closely to what I'm saying. For any number, num, two factors are fixed. Yes or no? As long as the number is not equal to 1. 1 is useless, remove 1. As long as the number is not 1, two factors are fixed. Yes or no? And what will those two factors be? 1 and the number itself, right? Now, moreover, the requirement of T prime is three factors and 3 is an odd number. So it is guaranteed that that number should be a perfect square. So that number must be a perfect square. So there must be a number x so that x into x is equal to num. But the important thing over here is that apart from 1, x and num, there should be no other factor of it. So there should be no factor found in this area and no factor found in this area. When is that possible? Under what situations that is possible? So I would say that is possible only if the square root itself is prime. For example, if you consider a number like 25, 1 and 25 are already the factors of it. And on top of that, 5 is also a factor of it. And apart from 1, 5, and 25, you can see there is no other factor of it. See, if the square root is not a prime, if square root is not a prime, let's say if you take example of something like 16, 1, 16, and 4. If the square root is not a prime, that means it's composite. So it can always be expressed as something into something. So this 4 can always be expressed as 2 multiplied by 2. So if 2 is a factor of 4, 2 will also be a factor of 16. Now the moment you have 2 over here, you will have 8 over here, right? So the property of t prime is that it should be a perfect square number, but the square root itself should be prime. And then that means if you list down the squares of prime numbers, if you list down the squares of prime numbers, they are all t primes. Can you note it? How many of you relate to it now? So in this question, there is nothing special that we need to do. All that we need to do is whatever array is thrown at us, we will iterate on this array, we will catch hold of a number, and we will find its square root. SQRT of AI. Let's say it is x. First, we will check if x into x is equal to AI or not. If x into x is equal to AI, then it is guaranteed that this number is a perfect square. But on top of that, we need to check if is prime of x is true or not. So if x is a square root of AI and x is a prime, then only this number is t prime. Otherwise, this number is not a t prime. How many of you understood it clearly? Now there is nothing special which has remained in this question because square root you can find using this SQRT. And in order to check whether something is a prime or not, can you use this pre-computation that you did in sieve, right? Can you use that? You can. Because instead of checking x is a prime or not, I mean, the brute force way of checking whether x is a prime or not could be by writing a for loop. But better way could be if you have done the pre-computation, if you have pre-computed the sieve, that pre-computation cost would have been n log n, right? So this is your pre-computation. And then what you are doing is you are iterating on the array, you are finding the square root, and then after finding the square root, you have that if check, if x into x is AI, and if this is, so that check happens in order one time. And what is the complexity of finding square root? Those of you who have learned binary search would know, but the complexity of finding square root, it happens in log of n time. Square root can be found out in just log of n time. So the complexity of this thing would be n multiplied by log n. So you can see your pre-computation cost is n log n and your query cost is n log n. So in n log n time, you will be able to solve this question. However, what was the basic idea? What was the most important idea? The most important idea over here was the moment you saw 3, lot of you agreed that, hey, odd, odd, odd. Okay, so yeah, so there has to be a perfect, a square root, a perfect square root. But then you missed this fact that that perfect square root must be a prime. If it is not a prime, then it won't work. So that's all. Yeah, you have to create C for the maximum element of the array. Yeah, you're totally right. So you would be given, so let's say you have been given that your array of I is smaller than equal to 10 power 6. So in that case, you can create a sieve array is prime array of 10 power 6 plus 1. And then you can fill it and then you can answer all these queries. Is that clear?